Welcome to this video on the topic of programmatic thinking, Lesson 2, Flowcharts and General Solutions. In this lesson, you will learn how to represent process using flowcharts, use conditional statements, and finally, you'll learn how to construct general solutions to nonlinear problems. By the end of this lesson, you'll be able to draw flowcharts to represent programs, you'll be able to use conditional statements to allow for choice, and finally, you'll be able to create general solutions to problems involving maze navigation. Part 1, Flowcharts. Consider the situation shown on this page. We have a Charmander in a maze. What we'd like to do is we'd like to write a program to help Charmander navigate from the start of the maze to the finish. Using our understanding from the previous lesson, what we find is that we can write a program as shown over here. Charmander need only move 3 tiles downward. Doing this, Charmander is able to finish the maze. Now this code over here can be represented visually using something called a flowchart. The flowchart is shown on the right. The flowchart itself is the visual representation of the code. The flowchart is made up of a number of different components. The first component we'll look at is the begin. This is equivalent to line 1. The circle that's shaded in represents that we're beginning a program, and then we've got the name on the right. Notice how the name here is the same as the name over here. This is because they're directly equivalent to one another. The only difference being is this is a visual representation, this is the code. The next block we'll look at is this block over here. It's a square or a rectangle with rounded edges. Inside we have a verb and a number. This corresponds to line 2 of the code. They're directly equivalent. Going down, we have this terminating block here, or end. This says that the program's done. We draw this by drawing a circle with a little dot in the middle. This corresponds to line 3. Connecting all the blocks together in the flowchart, we use arrows. The arrows denote the flow of the code. We always follow the arrows. Consider the problem over here. We have Charmander found in a maze once again. Once again, the objective is to help Charmander navigate from start down to finish. What I'd like you to do is copy this maze down into your book. Pause the video until this is done. Moving on. To generate a solution to this particular problem, because the maze itself is very similar to the first maze, we can actually reference our original program. As seen, we simply move down by 3. However, this isn't a solution to the problem itself because we're still not at the finish. What we need to do is we need to tell Charmander to turn to his left and then move across by 1 block. This is going to look something like this. Make sure that you copy this code down into your book. The next step is we're going to convert this particular code into a flowchart. This is shown over here. Notice how the complexity of the code has increased. Before we had 1 instruction, now we have 3. Consequently, the flowchart itself has gone from having 1 block to now having 3 instructional blocks. What I'd like you to do is I'd like you to copy this down into your book as well. So copy the flowchart down as if you did it yourself. Pause the video until this is done. Alright, moving on. Third example. We have Charmander and he's stuck in an even more complicated maze. What you're going to do is you're going to lead in finding a solution to this particular problem. What I'd like you to do is I'd like you to generate a code, or generate the code that's going to help Charmander navigate from here down to here. Pause the video until you've finished writing the code. Now your code should look something similar like this. Your code might be different, but if it works, then that's fine. What I'd now like you to do is I'd like you to change this code into a flowchart. Pause the video until you've finished drawing the flowchart. Your flowchart will likely look something like this. Notice that you have 5 instructions going on in here. 1, 2, 3, 4, 5. Consequently, you have 5 instructional blocks in the flowchart. 1, 2, 3, 4, 5. Observing the pattern of Charmander using this code, we find that he's able to navigate to the very bottom. Illustrating, what each individual block does during his journey. We have in green, he goes down by 1, he turns to his left as shown by pink, in blue he moves by 1, he turns to his right shown in purple, and then he goes down by 2 shown by the light orange. So what we've done over here is we've managed to create flowcharts, generating them from the code. Referencing our learning intention and success criteria, we're able to represent process using flowcharts, and we can definitely do that as we're drawing them now. Let's move on to part 2. Part 2, general solutions. In part 1, we came up with a solution to simple mazes. The first maze we looked at was simply a maze that had 3 blocks going downward or 4 blocks going down. All we needed to do to solve this was move 3 down. But what happens if we change the maze ever so slightly? So we've changed the maze in that we haven't really increased complexity, but rather we've simply increased size. Now what we want to know is, can we use the solution from over here to solve for the navigation of this particular maze? And what we're going to find is that if we run through this, then we find that it's not actually a solution. What we call this is a specific solution. Specific in that it only completes a very specific task itself. So even though the complexity hasn't really increased, only the size, we can't actually solve the problem, and that's not really what we want to do. Rather, what we want to find is something called a general solution. Now to do this, what we need to do is we need to use something called a conditional block, or a block where we can make choice. So moving on, we can do something like this. On the left here we have the program in its original glory, and on the right we've modified it. Now what you can see is that we're going to start here and we follow the arrows down. So the first block we come across is we want to move by 1. So Charmander is going to go from here down to here. After which we get to this block over here and it says if finished. Now looking at this, we're not finished because, well, he's not on the finish block. So that means we're going to pick no and we're going to go back up. We get to here and we run the code, move 1. So Charmander is going to move down again. Looking down, we ask, are we finished? The answer is no, so we go back and we're going to repeat this. We're going to repeat this until we find that we've actually got a solution to the first problem. But the question is, will this solution work for maze number 4 over here? And what we find is, well, the answer is yes, because what's going to happen is Charmander will start here and he'll go down. He's not finished, so he'll go down again, and down again. He'll only, or the program will only ever stop when we hit the finish block. Consequently, we find that we have what's called a general solution. General in that the program itself will work on more than one maze. Alright, if this works on these 2 mazes, then what about this maze? Well, looking at the first one, we expect the result to be true. But if we run this problem or if we run this solution on the second maze, then what we find is that, well, it doesn't really work because we tell Charmander when he's down here, he wants to keep running into the wall because he doesn't know how to turn. So what we need to do is we need to refactor the part of the code that doesn't really work. In doing this, we identify the part of the code that doesn't work by this light orange over here. Refactoring this, we need to add more choice. We need to think, what will we do if we can't move forward by 1? So we say, if the front is vacant, so if we can move forward, then we'll just move forward. Otherwise, we'll turn left. Observing the effects, what we can see is that we still have a general solution for maze number 1, and then observing maze number 2, what we find is that we go downward, so looking at pink, the front is vacant, we can move down. When we can no longer move forward by 1, we turn to the left, so we execute this part of the code. Going back up, we're not done. We go down, is the front vacant? Well, if we're facing to the left, then it means we can move 1. And therefore, what we have is a general solution for this particular set of mazes. So this program not only runs on this maze, it runs on this maze, and you can probably bet that it's also going to run on maze number 4 as well. So we call this a general solution because it works on more than one problem. So looking back to our learning intentions and success criteria, we set out to learn how to represent process using flowcharts, use conditional statements, and construct general solutions to nonlinear problems. It's at this point we realize that we're able to draw flowcharts to represent programs, use conditional statements to allow for choice, and finally we're able to create general solutions to problems involving the navigation of mazes. But we can go further than this. We can go into some refinement, because mazes aren't necessarily simple. Rather, we can go for mazes that look like this, and we can strive for a general solution here. Now, looking at this particular maze, what we want to do is we want to think, how can we modify this program over here so we can run through this maze? What I'd like you to do is I'd like you to pause this video, and I want you to come up with a solution inside of this flowchart. So how can you modify this section such that you're able to traverse this maze without breaking the previous mazes? Unpausing the video, let's have a look. What we have is we need to refactor this part of the code over here. This is done by checking what to do if the left square is vacant. So what we find is running this code, we first can move forward by 1 as shown by the thing because we're able to move forward, but then we come to a situation where we're unable to move forward, in which case we follow this branch of code down through this way, then we ask, is the left vacant? Because to our left this square is available, then what we can do is we can turn to the left as shown by the green here. We're not done, so we run the code back upwards. We then look again, is the front vacant? Well, because we're facing to the left, it is, so we can cross over. We then move by 1, going across and going back up. We're now faced with the situation where we can't move forward, so we don't know, and we can't move to the left because the left isn't vacant. In which case, all we can do now is we can turn to our right. This is shown by the orange over here. Turning to the right, we then free up the squares in front of us, so the front is now vacant and we have a clear path to the end. So therefore what we've done is we've found a general solution for this particular maze as well. Now using this program itself, we're going to find that we can also solve these particular mazes too. So what we're looking at is we're looking at how we can refine our maze problem so that it works in all of the other situations that we've seen before. Now what I'd like to challenge you with is, what about this maze over here? Consider what you need to do to this part of the program to enable you to navigate this particular maze. Going forward once more, once you can find the solution to this maze, what can you do to your program so you can navigate this maze? What I recommend is, can you preference the path least walked? In summary, what we had a look at in this lesson was we wanted to learn how to represent process using flowcharts. We wanted to learn how to use conditional statements, and we wanted to construct general solutions to nonlinear problems. By the end of this lesson, you would have demonstrated that you can draw flowcharts to represent programs. You should be able to use conditional statements to allow for choice within your programs. And finally, you were able to create general solutions to problems involving maze navigation. Well done.